Hi everyone, I'm Galois. Today I'm going to talk about the basic concept of EVM and how bytecode is formed and executed. Here's my Twitter handle. If you have any question, just DM me, or if you want to have a discussion with me, or if I say anything wrong about the EVM, just come to correct me. First, I want to thank Sunset for inviting me to make such a presentation. I think it's really important to me to make some presentation and do some writings because it helped me reconstruct my knowledge. I think it's really important for technical guys and researchers to do some technical writings, and in some way it will help us to reconstruct our knowledge and help us rethink and help us dive deeper into our technical stack. And I think practice makes perfect. Theory is theory if you do not put practice into it. If you want to dive deeper into the EVM, I think participating in some CTF games is a good way to start. In Istanbul, I met Juno, the CTF monster, and he said one of his teammates was reviewing the puzzles even when he was eating. I think all the CTF players do share one thing in common, that is that solving the puzzle might take some time or even take more time than you thought. But in my opinion, when I solve some puzzles, all the puzzle I make would become worthwhile. And if you want to go further, I think you should learn some DeFi hacks reproduced from Sunset's DeFi Hack Labs repo, which is one of my favorite repos on GitHub. Okay, let's start. Here's a picture of the EVM overview. The EVM is part of the Ethereum that handles smart contract deployment and execution. Simple value transfer transaction from one EOA to another EOA do not need to involve it, but everything else would involve the state update computed by the EVM. The job of the EVM to update the Ethereum state by computing valid state transition as a result of smart contract code execution as defined by the Ethereum protocol. This aspect leads to the description of Ethereum as a transaction-based state machine, which reflects the fact that external actors initiate the state transition by creating, accepting, and ordering transaction. We can see from the picture at the top level we have the Ethereum world state. The world state is mapping of Ethereum addresses, which has 160 bits value to its account. It's called account. At the lower level, we can see at the lower level each Ethereum address represents account comprising a balance, and the balance stored as the number of weight owned by the account, and the nonce is representing the number of transactions successfully sent from this account if it's an EOA, or the number of contracts created if it's a contract account. The account storage which is a permanent, the account storage, which is a permanent data stored only used by the smart contract. And the accounts program code, if only the account is a smart contract account, the account's program code will be used. An EOA will always have no code and an empty storage root hash. Let's go deeper into it. EOA is controlled by a private key. EOA cannot contain EVM code, as we can see from the picture. There are two kinds of accounts. One is called EOA, and the other one is called contract account. The two main differences between EOA and contract account is about the EOA. The EOA nonce start from 0, and the contract accounts start from 1. We can see from the picture that the EOA public key drive from the private key, and after the hashing method we get the 160 bits of address. But when it comes to the contract account, it depends on the create contract method. There's two methods to create a contract, but in this picture I just show you create method. But the new one to create a contract is called create2. When using create method to create a contract, the contract address is decided by the sender address and nonce. When using create2 method to create a contract, it's decided by the sender address and initial. When a transaction results in smart contract execution, an EVM is instantiated with all the information required in relation to current block being created, and the specific transaction being processed. In particular, the EVM program code is loaded with some code of with the code of contract account being called. The program content is set to 0, and the storage is low from the contract account storage, and the memory is set to all zeros, and all the block and environment variable are set. A key variable is the gas supplied for the execution, which is set to the amount of gas paid by the sender at the start of the transaction. As code execution progresses, the gas supply is reduced according to the gas cost of the operation executed. If at any point the gas supply is reduced to 0 and an OOG exception we call out of gas is immediately holds, and the transaction is abandoned. No change to the Ethereum state apply is something like transaction in some relation database like MySQL and PostgreSQL, except for the sender's nonce being included, and their either state going down to pay the block's resource used to execute code to the holding point. At this point, you can think the EVM running on a sandbox copy of the Ethereum world state with this sandbox version being discarded completely if execution cannot complete for whatever reason. However, if execution does complete successful, then the real world state is updated to match the sandbox version, including any change to the core contract storage data, like the picture show, or any new contract created, or any either balance was initiated. Transaction will change the world state when you send a transaction. It will change the world state, like account state will update if you do some ERC20 transfer. It will update the balance. Okay, let's go deeper to the EVM storage layout. State variables of contract are stored in the storage in a compact way. We can see this on the picture. So, multiple values sometimes we use the same storage slot, except for the dynamically sized arrays and mappings. Data is stored continuously item after item starting from the first state variables, which is stored in slot 0. We can see it from the picture. And for each variables, a size in bytes is determined according to its type. Multiple continuous item needs less than 32 bytes are packed into a single storage slot, if possible. According to following rules, the first item in a storage slot is stored low order allied, and value type are used only as many bytes are necessary to store them. If a value type does not fit, the remaining part of a storage code is stored in the next storage slot. Struct and array data always start a new slot, and the item are packed tightly according to this rule. Item following struct or array data always start a new storage slot. For contract and inheritance, the ordering of state variable is determined by the C3 linearized order of the contract starting from the most base word contract. If allowed by the above rules, the state variable from different contracts to share the same storage slot. I'll check it. Let's check it. The hello world contract. We can see that the bool XX1, XX2, XX3, XX4 are occupied, and XX5 they do share the same slot because all of them are less. The sum value of them are less than 32 bytes, but on in slot 4, we can see that the uint 128 is used because it's go beyond the bytes 32 bytes. It go beyond the 32 bytes if we adding it into slot free, so it occupied a new slot. Let's go to check the WAP Ethereum contract storage layout on Ethereum. Okay, let's open the link. Oh, sorry, it might take some time to. Okay, we can see the storage layout. We can see from the picture that the decimal occupied the slot 0x2, and the decimal of WAP Ethereum is 18. I want to say that most of the time we don't use decimal to use as a storage variable, but WAP either is a special case, so I will show you how to check the storage using the Alchemy or Anchor RPC to check the storage. Okay, I guess it might take some time because my network is not so good. Switch to JSON RPC and use this method, ETH get storage add, and we can copy the WAP either contract and then paste it into the possible argument and query the 0x2 storage slot and send the request. We can see that the result of the decimal of the 0x2 storage is 0x12, which is 0x12 in hex is the number of 18 in decimal. So we verify the store the slot 0x2 is correct. Let's go to see the storage slot of some mapping structure. We will go to query the 0x3. We can see from the result is a little bit different because the result of the balance mapping is 0, 0. That's quite common because mapping structure do occupy a slot, but it has a 0 value. The real calculation of the key value is using some other method to calculate the keycat 256 hashing result from to get the real storage slot. I will illustrate it. I will illustrate it by writing some code. Let's please just wait. Due to the unpredictable site mappings mappings and dynamic site type are not types cannot be stored in between the state variables preceding and following them. Instead, they are considered to occupy only 32 bytes with regards to the rules about, and the element they contain the stored start at the different storage store that is computed using a KeyCap 256 hash. I will show it later. Assume that the storage of the mapping or array ends up being a slot position P after applying the storage layout for dynamic array. The slot store the number of the element in the array is the length of the arrays. For mapping, the slot stay empty as is showed. We can check it from the rough either contract. The result of the 0x3 storage is 0. The slot stays empty, but it still need to ensure even there are two mappings next to each other and the content ends up with different storage location. Let's check the slot detail by writing some code to verify our algorithm. Please just wait me to open the code. Okay, let's get started. I will show you how to calculate the storage slot when it comes to the mapping structure of a contract. As we can see from the previous anchor response is the storage slot of mapping structure will be 0, and we didn't want to know some keys like some EOA account balance or some contract account balance in this warp Ethereum contract balance method. So we need to calculate the slot first. The rule, I'll just tell you how to calculate the storage slot directly. It's about the address you want to calculate, that it would be encoded in UIN 32 bytes like UIN 256, and what's next is the storage slot in this contract. If you want to query the balance of the slot will be 0x3, and then we can calculate the storage slot of the zero address. Let's check the result of attacking POW like here. Okay, the result will be 0x36173 blah blah, and let's go to verify it on the EVM storage website. Let's click the balance button. Yes, as we can see, the slot will be exactly the same as the result we calculated. When we want to query the balance of zero address, we just go to put the slot into the anchor and RPC and use the ETH get storage add method, and then we can get the zero address balance. Okay, let's continue. let's go further. Gas. Gas is a Ethereum unit for measuring or for the computational and storage resource required to perform some action on the Ethereum blockchain. In contrast to Bitcoin, in Bitcoin, the transaction fee only takes into account the size of the transaction in kilobytes. Ethereum must account for every computation step performed by the transaction and smart contract code execution. Each operation performed by a transaction or contract costs a fixed number of gas. Some example from the zero paper. It's like adding two numbers got 3 gas, calculating the keycat 256 hash costs 30 gas and 6 gas for each 256 bits of data being hashed. Sending a transaction basically costs 21,000 gas. There's a famous attack called Tangerine Whistle. You can go deeper to check the details on EIP 608. I can tell you something about I can tell you some overview about the attack. The attack is about a mismatch resolved by the hard fork codename called Tangerine Whistle. It was relative to the gas cause. When it comes to related to the gas cause, I will not go further, but you can check it on the EIP 208. Here's the basic compute unit. I think is about the basic compute unit of EVM. The EVM is a simple stack-based architecture. As we can see from the picture, it consists of program counter and some gas available variables, stack, and memory and storage to help them to calculate some unit. The stack is 256 bits. Read or write unit. We can calculate or do some operation. We do some operation on the stack, and the max length of the stack, the max depth of the stack is 1024 elements. Here's the EVM execution models. First, when we put some input bytecode on the transactions core data, and when the EVM execute model gets the gets the instruction or the operation by passing the input data, it will pass it into some operation, and if we call some contract, it will fetch the EVM code from the contract storage, and then it will maintain the program counter to calculate some what step we are going, and which line of what step we are going, and which operation we are heading for. And as the transaction progress, we will use some calculation by the help of stack, memory, and storage to do some computation. That's a simple execution model, but it deals with lots of state change. Okay, let's go to the next chapter. Here's how I will show you how bytecode is formed. Most of the time, bytecode consists of three parts of this: init code, runtime code, constructor, parameters. But in my opinion, this is a little bit single-sided. The runtime code is calculated by the EVM, and the returning value of EVM when sending a transaction of contract creation is exactly the bytecode of the runtime is exactly the runtime bytecode of the contract. Okay, I will illustrate how the difference between constant and immutable in Solidity. When it comes to immutable, I will only write some codes about immutable. I think it's better it's better to leave the constant one to you to verify your ideas or your discovery. So let's get started. I'm too lazy to create some new directory. So it's about some. I will write some codes about it. Constructor. Will use some variable like uint 256 public number and is immutable. Yep, in constructor we will set the number as 0, then we compiled it, use forge build. Let's check the result. Of this contract. Compile the result of this contract. Yeah, is heroes.json. I will copy the bytecode and pass it to the EVM codes website, which is one of my favorite websites too, and then click the run. I will go. We can see the return value. We can see from the return value that the bytecode is a little bit different from the compiling result. We can see the prefix is exactly the same, but when it comes to the number, when it comes to the prefix of the bytecode is exactly the same, except this one. In compiled result is 0, but in return value is 2. This is because we the compiled result is just compiled result. It consists of 2 parts, and in the code we can see from the previous keynote that the layout of the bytecode, the init code is where we put some parameters, or we put the parameters from behind the runtime code. Is that the precompiled result? We did not take the set the number into this step into consideration. So the result it will be slightly different from the result as is compiled. So the constant one, I will leave it to you guys to verify your proof. Here's my presentation reference. I think is pretty helpful when debugging some puzzles or solving some puzzle, and it's really helpful if you want to go deeper into the EVM. That's all my presentation. Thank you.